Okay, now that we've done the derivatives with implicit differentiation, and we've seen a couple different techniques, we've practiced that a little bit. Now what we're going to do is we're going to come back and we're going to talk in general about the derivatives of inverses, and specifically the derivatives of the inverse trig functions. And so that will kind of round out and finish up all the derivative rules that you will need to have memorized. Now just kind of remember that whenever we have an inverse function, that an inverse function is a function that will undo whatever the original function did. And so just a reminder, our inverse function, which we're using our notation f inverse of x, will undo the work of f of x. If you remember, if we were to do a composition of the inverse with the original function, the inverse will undo the work of f and you will return x. And we also know that our f of f inverse of x is also equal to x. It's kind of our definition of inverses, that they will undo each other. All right, now of course not every function has an inverse function, only some of them do. Let's take a look. Simple case, if I wanted to find the inverse, and it's in the numerical notation with points, then I know the inverse of this would be 5, 2, 6, 3, 2, negative 1, and 7, 4. That an inverse, what it does numerically to the points is it switches x and y. Okay? That the idea is that if we know that x, y is on f of x, then y x, oops, let's make that a comma, then yx is on f inverse of x. And I'm going to call these points a very special name. These are going to be called corresponding points. This is going to be important for when we start to find the derivatives of these inverse function. We will have to have this idea that our corresponding points, that we were basically here finding f inverse of x is y, which would tell me that f of y is x. All right? Corresponding points, that f inverse of x is exactly your f of y. Okay? That these correspond to each other. All right? So we want to keep that in mind, corresponding points. Since switching x and y is how we find the inverse, if I wanted to find the inverse of the simple linear function, y equals 5x minus 8, switch x and y, solve for y, x plus 8 over 5, and then rename it as the inverse, f inverse of x, x plus 8 over 5. All right, just a quick review of inverses. All right, so a function g of x is the inverse if f of g of x and g of f of x equals x, okay, which is what we highlighted above. And we want to make sure that we recognize the domain of f is the range of g, the domain of g is the range of x, that if you switch x and y, you are switching your domains and your ranges. Your x values become the y values and vice versa. If you have a vertical asymptote on f, it's a horizontal asymptote on g, etc., etc. And if f of a equals b, that means g of b equals a, that we have corresponding points. Corresponding points. You are going to keep hearing this comment, this notation, to recognize that if I have AB, then I know BA is on the inverse. If I know BA is on the inverse, I know AB is on the original. Okay? When will a function have an inverse? When it is 1 to 1. That each x goes to only one y, each y goes to only one x, passes the horizontal line test. So if you have a function that passes both the vertical and horizontal line test, then it will have an inverse that is a function. And that's going to be kind of a key to what we're looking at. All right? Now, here's what we're going to talk about kind of in theory a little bit, just to kind of give you an idea of what really is happening when you do the inverses and what happens to the slopes of their tangent lines. Okay? So the first thing is that what you want to do is you want to think about, let's pick two corresponding points. So I'm just going to pick these 2 points. And first off, how do I know that they are corresponding points? Remember that when you have a point AB on f of x, that if you are going to switch x and y, so in this case I'm specifically going over 1 and up 0, that to get to the inverse you switch x and y. So it becomes BA over here, the corresponding point. And in this case that would be 0, 1. Okay? And so remember, we are reflections. This function, all I'm basically doing is reflecting it over the line y equals x, which is that switch x and y. Now let's think about the slope, because what we're really interested in is finding the slope of this tangent line and talk about how is it related to the slope. Kind of extend this out here, and let's change color so we can see the difference. And the slope of this tangent line. I want to see what the difference is. Okay. Now let's think about how we calculate slope, just a kind of idea, this switching x and y that's going on. So right now, to calculate this slope, say down here for this one, we would calculate our change in x and our change in y, right? So the slope, just thinking rise over run, is going to be, in this case, just eyeballing it from what I have, my rise is about 2 and over 1, so it'd be 2 over 1. So the slope of the tangent line to f is going to be 2 over 1. But now think, what did I do? I switched x and y. So the change in x becomes the change in y on the inverse, because I switched x and y. The change in y becomes the change in x on the inverse. So now if I wanted to do the slope of the tangent at the corresponding point, notice that all you're doing is now it's still rise over run, but now this rise was the old run, and the run is the old rise, which is 2, because you switched x and y. And the key is, what is the relationship between the slope of the tangent on the inverse and the slope of the tangent on the original function at corresponding points? Inverse functions at corresponding points have reciprocal slopes. That all you're doing is interchanging x and y, so you're interchanging the rise and the run. So inverse functions at corresponding points, that's the key, have reciprocal slopes. Notice this one is going to be the slope at f inverse of 0. Okay, so let's think about that. F inverse, the slope at 0, is going to be the reciprocal of the slope on f at the corresponding point. The corresponding point to 0 is 1. Inverse functions at corresponding points have reciprocal slopes. The slope on the inverse at 0 is the reciprocal of the slope on the original at 1, the corresponding point. And it's repeated 3 times because that is all you need to remember for this. Inverse functions at corresponding points have reciprocal slopes. So mathematically, taking a look at how we're going to write this formula, and this is basically a formula. You're going to see this question in multiple choice and possibly one part of a free response. And when we are doing inverse functions in general, you pretty much just need to memorize this formula, that f and g are inverse functions. We know that f of g of x and g of f of x equals x. We know that f of a equals b and g of b equals a, that we have corresponding points. Corresponding points. All right. Then I want to find the derivative on an inverse at b. So I want to find the slope of an inverse function at b. The slope of an inverse function is the reciprocal of the slope on the f, the original function, at a, the corresponding point. The corresponding point. Now, you'll see this formula written several different ways, mostly because of notation. Like I've set it up so that I can basically use A and B here. But a lot of times what you'll see with this formula, it will be alternatively written as G inverse of X, because B is the X on the inverse, equals the reciprocal of F prime of, and what's the corresponding point to X? How do you actually find the Y value, the corresponding point? You do G of X. So you'll see the formula written like that. That what you want to do, the X and G of X, that's finding the corresponding point. So the slope at X is the reciprocal of the slope at the Y value from X, the corresponding point. You can also see this written as F inverse of X, because G is the inverse. So maybe they like to use this. And then we need to make sure we're doing the derivative. So the derivative of the inverse at X is the reciprocal of the derivative of F at F inverse of X. So I think this is a confusing formula, mostly because of the notation. But all you have to remember when you are doing these problems is that the inverse functions, the derivatives of the inverse function, the slopes at corresponding points are reciprocals of each other. All right, so let's take a look at a couple of examples and see what happens here. So we have this function. We're going to start with a nice simple function, 2x cubed plus 1. All right, so the first thing they're going to have me do is they're going to have me find f of 1. Straightforward. You're going to plug in 1. 2 times 1 cubed plus 1 is 3. Notice that what you're doing here in this A is really finding a point that's on F. All right. Now they want me to find F prime of 1. All right. To find F prime of 1, I'm going to first find F prime of X. So that would give me 6x squared. So F prime of 1 is going to equal 6. Right. Then we have C. I want to find the inverse of the function. So find F inverse of X. We're going to switch X and Y. And this is more work than you would do when you're doing this. We're just doing all the parts to kind of show you how it fits together. So I have Y equals 2x cubed plus 1. Switch X and Y, 2y cubed plus 1. Subtract 1. Solving for y now, divide by 2. Take the cube root of both sides. And this is going to be my F inverse of X. All right? So part C, we found the inverse. Now I want to find F inverse of 3. So F inverse of 3. Well, if you think about it, you don't have any work to do, but if I were to plug 3, 3 minus 1 is 2, 2 over 2 is 1, cube root of that is 1, but didn't we already know this? This is the corresponding point to the fact that 1, 3 was on f of x, which we already knew from A, so 3, 1 is on your inverse. Okay, just getting all our relationships down. All right, and then so all of this is just some pre-work for us. Now here's where the problem comes in. I want to find the derivative of the inverse at 3 two different ways. Okay, so method number 1 in this E, I'm going to find f inverse, the derivative, at 3 by using the rule that is above. That's actually the short way, even though you're like, what? The slope on the inverse is the reciprocal of the slope on the original at the corresponding point. The corresponding point is 1. Right? And since we already calculated this, f prime of 1 equals 6, so this would be 1/6, and we get to walk away from the problem. Look at how fast that was. Notice I didn't actually have to find or use the information that I had in C. That this C was kind of completely unnecessary. But the point of this formula is even if I know f of x, but I want to find the slope on the inverse, instead of, which is I'm going to do the second option, instead of finding the inverse, finding the derivative of the inverse, and then plugging in 3, if I already have information about the original function, and I already know the derivative of the original function, I just simply have to go, the slope on the inverse at 3 is the reciprocal of the slope on the original at the corresponding point 1. Right? So that's the short way of doing this. Now let's take a look at the long way. So short way. The formula is the short way. All right, so now let's do the long way. Long way. Now remember, the reason why this is the long way, right? So short way, use formula, slope on the inverse is the reciprocal of the slope on the original at the corresponding point. Right? Which only required that I know what the corresponding point is and I know the slope on the original. Right? The long way would have been to first find f inverse of x. So the long way would have to do part C and get our inverse function. And I'm also going to rewrite it because the next part of this, after I've done all this work, is that I now need to find the derivative of the inverse function. So I need to find f inverse prime of x. So let's go ahead and do that. Let's use our power rule and chain rule. 1/3 x minus 1 over 2 times the derivative of this. Remember, this is just 1/2 times. So it would be 1/2 x minus 1/2, which is just 1/2 for its derivative. All right, so we would end up with 1/12 times x minus 1 for our derivative. And then now, once I have got all the work for finding the inverse, switch x and y, solve for y, then I find the derivative of the inverse, have that here, then I'm ready to go f inverse prime at 3. The slope on the inverse at 3 would be 1/12, 3 minus 1, which is 1/12 of 2, or 1/6. Same answer that we got before. So the idea is that the formula is a shortcut for us to find the inverses. Now, let's come back up here and let's kind of talk about the steps to this. When you are using this formula, the slope on an inverse at B can be found by doing the reciprocal of the slope on the original at the corresponding point A. So step 1 of this method is to find the corresponding point. In other words, you have to take your B here, and you're basically going to find G of B equals A. That's step 1. Step 2, that's when you are going to do the reciprocal of the original function slope at the corresponding point. So you take I want to find the slope on the inverse at B. I have to do the reciprocal of the slope on the original at the corresponding point. So you find a corresponding point, and then use the original to do the problem. Right? Let's look at another example. All right, so now we have x to the 5th plus 2x minus 1, and that's f of x. So we're going to use the derivative of f of x, and we already know some information about the continuity. We're going to kind of talk about continuity of f of x to determine if f of x is 1-to-1. Now, and this is kind of a side thing, that in order to be 1-to-1, you have to pass the vertical and horizontal line test. Well, to pass a vertical line test, a function has to be monotonic. Either monotonic increasing or monotonic decreasing. Now, this is an x to the 5th with a positive lead coefficient, so we need to show that this is monotonic increasing, because if it went up and then came down, then it would fail the horizontal line test. So if we can show that this function is always increasing, then it would clearly pass the horizontal line test, which would mean that it is definitely 1-to-1. So let's think about how can we show that a function is always increasing by using its derivative. You can show that its derivative is always positive, okay? So first off, f of x is continuous because it's polynomial. And if it's continuous because it's polynomial, that would mean that it is also differentiable. Right? So that means we have a derivative. We can take the derivative. Our f prime of x is going to be our 5x to the fourth plus 2. And at this point, just by looking at this clearly, f prime of x is greater than 0 for all x, because you take any x raised to the fourth power is positive times positive plus positive. So if f prime of x is greater than 0 for all x, therefore, and we can conclude f of x increases for all x, and then the final result of that is therefore f of x is 1 to 1. That it increases the entire time, so there's no way that it's going to fail the horizontal line test. And if f of x is 1 to 1, we can now say f inverse of x exists. We have an inverse. Okay? So all of that was A. Alright, now that we know that we have an inverse, what we're going to do is, our goal is really to ultimately find here in C the inverse's slope at 2. I'm going to put that down first, because usually the problem doesn't say, hey, find f of 1, then find this. Usually the problem says, I want to find the slope on the inverse at 2. In order to find the slope on the inverse at 2, I'm going to do the reciprocal of the slope on the original at the corresponding point. Okay? So that's where you're going to be like, okay, the corresponding point. They're having you find f of 1 first, because let's think about this. Let's look what happens. F of 1, going back to the original function, plugging in 1, easy. 1 to the 5th plus 2 times 1 minus 1 is 2. Okay? So what this gives me, once I find this, is that the inverse, if I plug in 2, is 1. This is my corresponding point. Right? And so that's the idea. If I want to find the slope on the inverse at 2, what I need to calculate before I can do that is I have to find the corresponding point. I have to find the y value on the inverse at 2, which I can usually figure that out using the original function. Okay? There are times when they do these problems, you might be going like, well, how am I supposed to find f inverse of 2 if I don't have the inverse? A lot of these are going to be like a guess and check thing, where you're going to be like looking at it going, I need to know, basically when I'm doing this, you're kind of going, I need to know when f of x equals 2. I need to know when 2 is the output of f of x, and I need to solve for x. And a lot of times when you see this type of a problem, you're like, well, it's an x to the 5th. How am I supposed to know that? Usually they're easy enough that you can guess and check. That you kind of, if you look at this, it's like plugging in zeros, ones, negative ones. It won't be anything out of the range of like -2 to 2. You just kind of eyeball it and go, oh, I can kind of tell without doing any work that if I go 1 here, that would cancel a 1 there. You can kind of guess and get at x equal to 1. Just warning you, because you'll be like, I don't know how to solve that. It's guess and check. Look for the most obvious answer when you see this. Okay? So that's kind of this idea kind of we're leading you into, that if I want to find this, your step 1 is find the corresponding point, which means you're trying to figure out when you plug 2 into the inverse, what do you get for your output, which is the same as saying 2 is the output on the original. What did I get for my inverse? And so now we can do 1 over f prime of 1, and that is really easy to calculate. I already did that up here for the derivative, so I just go 5 times 1 plus 2, which is 1/7, and then we're done with the problem. So notice I did not actually find an inverse, plug 2 into the inverse, then find the derivative of the inverse to then plug in 1. So I didn't actually have to do all that work. You just have to kind of see the connection on this. Okay. Let's see, did I do everything it asked me to? Yes. So now what we're going to do, let's come down and do example 4, just to kind of show you some things that you might see. So notice that it's giving me this information right here. The reason that it's giving me this information is that the composition of m and n and m equals x, then m of x and n of x are inverses of each other. So this is one of those things that you kind of just have to recognize, like in a multiple choice question. Oh, they're inverses of each other. Now notice that they gave you m of 5 equals -9. So you should be able to immediately go for the corresponding point, just to kind of make your note that if I were to take the inverse function, and plug in -9, then I would get 5. Okay? So based on the fact that they are inverses, I can figure out corresponding points. Right? They also gave me that the slope at 5 is -8/11 on m. And notice, what are they asking me to find? They want me to find the slope on n at -9. So I go, well, the slope on n can be found by doing the reciprocal of the slope on m at the corresponding point. The corresponding point to -9 is 5. Oh, wait a minute, they gave me that information, which is the reciprocal of 1 over -8/11, or -11/8. So the idea is to remember that if what you are looking for is an inverse, to find the slope on an inverse, you do the reciprocal of the slope on the original function at the corresponding point, over and over and over. Okay? Alright, so we're going to stop this video at that point because I want to do the inverse trig functions as a separate special case. But we'll stop there, and then we'll give you a chance to practice the inverse formula on generic inverses.